Okay. Now second question we will solve on the topic on thermal conductivity. We have got the question 2. It states that the steady state temperature distribution with linearly increasing. Rate of energy generation per unit volume with wall thickness within the plate wall given as 10 centimeter thick with a thermal conductivity of 9.3 watt per meter Kelvin as a function of position as follows. Okay. A function of position as follows. Conductivity is 9.3 watt per meter Kelvin. We have got this function of zero, 1, 2, 3, 4, 5. We have got different values in it. 145, 146, 165. We have to find these values. And we have got 1329, 1810 and 2405. Where Z is the distance measured from one side of the ball. Determine the temperature labeled with a question mark and the table and the rate of energy generation per unit volume at a 5 centimeter within the ball. We have to also find the rate of energy generation. We have to find this. Okay. Okay, let's start. We know the Fourier's law of heat conduction. It states that heat flux is directly proportional to the temperature gradient. It is given by this equation. It is given that it is linearly increasing. Which means it is linearly increasing. It can be the equation of straight line. Y is equal to mx plus c. In this case, I am assuming mz plus c. We have got G equals mz plus c, and we know that dq dz dz. Putting this in this, we got mz plus c equals minus d by dz. We know that q, what is q is Fourier's law of heat transfer. This only this, we are just solving it. Okay, dt by dz. We have got nz square by 2. Integrating with respect to x, we got this dt by dz. Again integrating with respect to x to eliminate this a differentiation term. We got mz cube 6cz square by 2 plus, here I forgot the integrating constant, plus cz plus c double dash equals kt. We have got the equation mz cube by 6 cz square by 2 plus cz dash plus c dash plus kt. Put dividing by k, we get m by 6 z cube plus c by 2 z square c dash plus c double dash. This is a equation. Now we are one by one of putting this value in this to get the value of constant. This is z centimeter. Putting the first condition, case 1, putting z equals 0, t equals 145. We got c double dash as 145. Case 2, putting z equals 10, this condition, t equals 2405. Putting this value in this, we got 2405. We know the value of c double dash. I am taking this side, 145 m by 6 z square plus c z square to c double dash. Dividing whole equation by z equals 10. Putting the value of z equals 10. We got 2405 minus 145 equals, putting z is 10 cube is 1000, 10 square is 100. We have got 2260. Solving, taking 10 common, this we got the first equation. Putting case 3, z equals 1, t equals 146. 146 minus 145 plus m z square by 6 cz square by 2 cz got 1 m by 6 c by 2 cz. This we got the second equation. We have got the case 3, putting z equals 9, t equals 1810. Putting this in the general basic equation, we got This one random multiplication and division. This we got the third equation. Solving 1, 2, 3, we got the values of m equals 12, c equals 6, c dash equals -4. Putting all the values in the main equation, we got T equals, we know about, we got as 2z cubed plus 3z square minus 4z plus 1 4. From here we will get to know the value of z equals 3. It is given a thermal conductivity is 9.3. We assume m equals m dash into k, which is equals to 9.3 into m. We got is 12. 111.6. We got the value of c is 6 into 9.3. We have assumed this. In start, we know the equation of linearly increasing straight line was mz plus c. We got the value of mx 11.6 to z, z at a distance of 5. It was given in the question, plus 55.8. We got the value of heat generation 613.8 watt per meter cube. We will move to the next question. Thermal conductivity question number 2. A plane wall with a surface area of, we have got the surface area is 30 meter per second square. 30 meter square, and a thickness of 20 centimeter, which is equals to 0.2 meter. Separates a hot fluid at a temperature of 170. A hot fluid is maintained at 190 degrees Celsius from a cold fluid. Cold fluid is maintained at 15 degrees centigrade. Under steady state condition, the temperature distribution across wall is given by, we have got a temperature distribution across the wall, which is the thermal conductivity of wall. We have got the thermal conductivity of the wall is watt per meter Kelvin. We have to find two things. Calculate the average heat transfer coefficient at the, we have to calculate the average heat transfer coefficient at the hot side and average heat transfer coefficient at the cold side, and determine the rate of energy generation. We have also determine the energy generation. First we will write the given data in the side, so we can solve the question in the remaining space. We have got 30 meter square per area per meter square. Thickness we got 20 centimeter. Hot fluid temperature 170. Cold fluid temperature we got 15. Temperature distribution, which is important, we got thermal conductivity we got. We have to first find the average heat transfer coefficient at the hot and the cold surface. Okay, let's start with the diagram. We have got the thickness as 20 centimeter. Okay, thickness, heat separate side, this is from cold side. Temperature of the hot side is 170 degree, temperature of the cold side is 20 degree. Where we know the Fourier's law of heat conduction, which states that heat flux is directly proportional to the temperature gradient. At first we are calculating at hot surface. Hot surface means at x equals 0. At x equals 0, we have to find the dt by dx at x equals 0. We got minus 600 minus 100x at equals 0. We got the value as 600 Kelvin per meter. Fluid at hot surface. Minus k dt by dx. We know the value of k, it's 10. We have just put the value in this, minus 600. We got 6000 watt per meter square. We have to find the value of heat transfer coefficient of hot fluid. So hot minus temperature of initial temperature. Then we need to find the temperature of hot fluid. Alright. Initial 0. So we putting the value of x, we got the temperature x is 150. Okay. Substitute the value. T is hot minus T naught. We got the value of hot. Have the heat transfer for the hot side will be Q upon T hot minus T naught. We just calculate the value of Q of the hot fluid and the temperature of at 0 degree at 0 centimeter from the wall is 150. After calculating we get 300 watt per meter square Kelvin. And the hot surface. Now we will find the temperature at cold surface. Means S equals to 0.2 dt by dx 0.2. We will get minus 620. Flux at cold surface. Minus k dt by dx. We know the value of k is minus 10. We just put this value. Got 6200 watt per meter square flux at cold surface. Now we have to find the value of heat transfer coefficient at the cold side. We know the formula. It's Q H T at 0.2 minus T cold. First we have to find the value of T at 0.2. So 150 minus 600 0.2. Putting the value of 0.2 in the temperature distribution curve. We get as 28 degrees Celsius. Putting this value in this, we get the value of H cold, which is Q upon T 0.2 minus T cold. It is 6200. We have just calculated 28 minus this 15. 477 watt per meter square Kelvin. Now we have calculated the heat transfer coefficient at the hot and cold both the side. We have to find the third part, which is rate of energy generation. It's q minus k d square t dx square. We know the value of dt by dx minus 600 minus 100x d square t dx square, we know it is minus 100. Putting this in this, we got the heat generation as 1000. This is not the heat generation. We will multiply this heat generation with its surface area. So we got the final heat generation as 6000 watt. We have solved all the first, second, third part. Now we will do the question third on this topic. Question third on the thermal conductivity. One side of a copper slabs receive a net heat at a rate of 5000 watt. We have got a net heat from one side. What due to the radiation? The other face is held at a temperature at 35. The temperature of the surface is held at 35 degrees centigrade. If the steady state condition prevails, calculate the surface temperature of the side receiving a radiation energy. The surface area of each face is, we have got the surface area of each plate is 0.5 meter per second meter square. We have got the plate thickness as 4 centimeters. First we will draw the figure. It states that one side of a copper slab, this is copper slab, receives a net heat input at a rate of 5000 watt. This is right, and the other surface it's maintained at 35 degree centigrade. We have to find the surface temperature size receiving radiation energy. Okay, we know that rate of energy in equals rate of energy out, which is given as 5000 watt. Then we find the flux. Flux is its rate upon area. We have got the area as 10,000 watt per meter square. Using the Fourier's law, using Fourier's law we know that K dt by dy integrating dt by dy minus K dt. We know the values qy, putting from 0 to 0.4 minus K. We know the other surface temperature dt. After solving we get to 0.04 minus K, 35 minus T naught, we got this 4000 minus 35K plus K T naught. After solving from this we get at K 398. We know 930 K. Now we know the average, the temperature of the other side of the slab will be 45 degrees centigrade.